Hey folks, I want to talk about our last decay mechanism, and then we're going to go through a few example problems. So the last thing we'll talk about is gamma emission. And typically there's lots and lots of ways that gamma emission can result. So by definition, it's a spontaneous emission of light, and that is a gamma ray. So recall, gamma is one of our most energetic things in the spectrum next to X-rays. And this comes from an energetic nuclear decay process. So one example of this, which again is kind of a rare, weird example in chemistry, this is known as annihilation, where we have an anti-electron colliding with an electron. Those things annihilate each other and release a huge amount of energy in the form of gamma. Okay? So like I said, this is very, very rare in chemistry, but as we start talking about fusion and fission, we see gamma start emerging a lot more. Okay? So let's do some reactions to make sure we've got these mechanisms down. Okay? So write a balanced equation for the following. So here, that's beta decay of, this nuclide is called tritium, so that's a hydrogen with 1 proton and 2 neutrons. And so let's do that. Let's just get straight into it. So we'll say 3, 1, H. So again, 1 proton and 2 neutrons. So 1 plus 2 gives us 3. So that's where that mass number comes from. And so because this told us it's beta, right away we'll just write the symbol for a beta particle, 0, -1 e. And we remember that these mass numbers and atomic numbers have to add up. Okay? So, for example, I've got a 0 right here in the mass number, and I know that it was a 3 to start with, so it's going to have to be a 3 to end. And then now I've got this -1 right here, and so that for my mass number, and so my mass number of my other nuclide is going to have to be 2, right? 2 minus 1 gives me 1. And so now I have to consult the table to see which nuclide I made. And we could see right there element number 2, so that would be helium. Okay, so that's our balanced reaction for beta decay of a tritium nucleon. So now our next example here, we've got lithium 8, and this is a beta followed by alpha. So we'll start by writing our lithium nucleon. And first it's a beta, so we'll write down that symbol for beta decay, 0, -1 e. And now our resulting, our other nucleon, right, has to add up. Okay, so that's going to be an 8 in the mass number, and it's going to have to be a 4 in the atomic number. 4 minus 1 gives me 3, 8 plus 0 gives me 8, right? And so now I look to see which element I made, so that's element number 4, which is a beryllium. Okay, so now that's a beryllium. And so now this says followed by alpha. So now we're going to get another reaction here. And so when we make an alpha particle, we need to recognize that's a 4, 2 helium. And if you notice, you can actually see, now hopefully you can see why this lithium 8 would undergo beta decay followed by alpha decay. Because now if you look at what remains, okay, it's got to be another helium nuclei, right? 4 plus 4 gives me 8, 2 plus 2 gives me 4. So this beryllium 8 is unstable and falls apart into 2 alpha particles. Okay? And so our final one here, positron emission on boron 8, okay? So we recognize that that's going to release a positron, which is 0, 1, e. And now, once again, all of our mass numbers and atomic numbers must be conserved. So we're making an 8 right here, and this is going to have to be 4. 4 plus 1 is 5, right? And we can see we made element number 4, which is beryllium. And even though it doesn't say, that it'll be followed by alpha, we can conclude based on this reaction that our previous reaction that it seems like alpha decay of this beryllium-8 nucleon is likely. But I'm not going to write that down just because the problem said, positron emission. Okay. So again, these reactions are pretty easy to balance once you know how to add up all those mass numbers and atomic numbers. So just make sure you're familiar with that and that you're able to do this in preparation for the exam and final. Okay. I'll see you in the next video, folks.